So, and then who our alumni here for putting this program together with Nigerian State of Engineer, Ikeja branch. For us, the program that we run based on current mandate and NUT mandate requires industry input in the training of our students, such that when they finish, they will be suitable for the industry. The industry is expected to work with us through this channel. Through participatory teaching, if the opportunity is there,
I would like to people a cultural that I support is related to questions that I would like to go from and you this type of people for this group guys exposed to cultural and for exactly just
Good afternoon, everyone. I am Luis, American citizen, and I'm the technical director at CFI. But I also like to mostly keep my busy with the details. I'm still designing platforms and looking at this particular situation, which is not uncommon. The worry that a pipe can give in and get all wrinkled up because of overstress. So we're gonna with the presentation. You can start. Okay, so you can see that now this sort of engineer, we use strong materials, and most of it steel or other materials that have high endurance, steel, concrete, and in the case of these materials, we recognize that we because they have strength and they have reliability and safety and long life. So we want something that lasts. The buildings must last many years, some over 100 years. There are some Roman built domes in Italy, one of the famous one that is only concrete, no reinforcement, and it's been there for 2,000 years. So the quality of the material. So it is for our offshore oil and gas business, because most offshore platforms have a design life of 25 years. So the steel that we talked about nowadays, there are different grades. In Norway, it's a higher strength steel, like 350 megapascals from 50 to 55 psi. And if you look at the steel behavior, it has 2 points of interest. One of them is point B, which is the yield strength. And normally, under normal conditions, you want to design to the yield strength with a margin. You never go over the yield strength because you want to remain on the elastic range. Because as you apply load from zero, lower level, the stress increases toward A, and you should stop around A to give that little margin for uncertainties before you continue on to B. Because if you stop at A and you release the load, it comes right back to zero without any permanent deflection. If you go close to B, it will start having a permanent deflection. When it comes down, it will not come down or following the line. It will come down in a straight line, which will fall a little bit ahead of zero on the bottom axis on the strain. So we don't want that. So that's why we have to give limits and consider this. But the two states, as it says, then is the yield state, point B, and then the ultimate tensile strength, which is D. Beyond D, the thing has given up in resisting anything and it's just gonna. So that beyond to E is called the plastic range. Before B is the elastic, where you know it comes back to the way it was before it was loaded. But if you go beyond that, it will not come back the same way. It will have a deflection or deflection. Next one. So the title here for this meeting is buckling. buckling is another one of the outcomes of stress or overloading, and is related to this ratio, the slenderness ratio, which is the length of non-supported column, or whether it's vertical or horizontal, is the same thing. If it's under compression from both sides, it will try to shrink, so it will have a tendency to buckle. So you apply the load, and the thing will resist to an extent, depending on how long is that length without any lateral bracing, and then the ratio between the moment of inertia and the cross-sectional area under the square root. That is called the slenderness ratio. That's very important in columns. So if a column is slender, which means it could be big but very long, it becomes slender, is susceptible to buckling failure. If it's a short column, it can withstand a lot more load like on both ends without buckling. So you can imagine, for example, a drinking straw. If you put it with compression on both ends and you start pressing on it, it will not take much force for the straw to just bend in the middle, crinkle and buckle. But if you use say a PVC pipe, a little bigger, it can be a lot longer to resist that same compression, and nothing will happen to that pipe because of the slenderness. That pipe is much less slender than a drink straw. Next one, please. So there are then two types of buckling. Is a local buckling due to bending, and then there is a buckling subject to hydrodynamic collapse. The local buckling is what I'm talking about. The column under compression can start bowing to one side or the other, and if you keep on applying load, that bowing gets shorter and shorter radius until it just crinks in the middle, it wrinkles in the middle, and then it collapses. Basically, the top part bends over the bottom part. The hydrostatic buckling is really the collapse that you may have when you put empty pipes at big sea depths, big depths where the water pressure acting on the outside of the pipe is much greater than than the internal pressure of the pipe. Whether it has product or is empty, the difference in pressure can cause the pipe circumferential shape to be squeezed down until it basically flattens itself in an implosion. The outside pressure wins over, the stress is exceeded, which is what keeps that circumference a circumference. It will start becoming elongated a little bit and then will collapse almost into a flat bar shape. That is another form of buckling collapse. So you can, in the first one, you can control that by making sure that your slenderness ratio is low enough where the pipe can stand the load that you want to apply without buckling. Buckling might happen even before you reach yield because it's a function of that ratio of the length, unsupported length over the radius of gyration. In buckling is different. Buckling will have to go through yield, and once it collapses, the pipeline can collapse for a quick length, collapse very quickly like a falling domino set. It will collapse in a row very quickly until it finds something where that buckling can stop, like a flange or an arrestor that they can put on the pipelines to stop that flattening phenomenon. So the two sides, when it collapses, they call it a bone or a dumbbell shape, which is similar to just the two sides becoming flat against each other. Next one. So on the left, you see a pipe with a dent, and that dent could be considered because something hit it on the outside, or some other problem during construction or whatever. That dent already created a weak spot on the circumferential shape of that pipe. So if a force is applied in compression, the pipe can bend around that dent. It can wrinkle and have a sort of a V bend in there, and it will fail through there. Or if you apply bending on a straight pipe and it bends because in subsea pipelines, the currents sometimes take away the support of the sand underneath the pipe for a certain length. It becomes a free span. So the pipe under its own weight and the weight of its contents can start bending downwards by force, like a beam between two supports. And you can see in the model that the straight pipe has no difference in stress one way or the other, is the same. But as it's bending and you get to the bottom section, you can see that the top part of it is starting to form waves, which is an indication that it's already buckling. If you continue bending it further down or applying axial force, it will buckle quicker after that. Those bends happen because maybe one of your structural engineers can tell me what happens when you bend a pipe, as far as what happens on the inner side of the bend and the outer side of the bend as far as stresses. Can you tell me what's happening on the inside of the curve as the pipe is bent? The surface that is on the inside, the one that's getting the waves. Why is it getting the waves? Yeah, that's because the load is pushing it down. But what causes the material at the surface starting to wave as it bends? Of the pipe itself, yeah. The material, yes, as it bends, the part that is on the inside of the curve feels compression. From both sides is compressing, is trying to crash into each other. Yes. Whereas on the outside, it's tension. Yes. It's stretching. Yes. So the outside will never buckle. Yeah. The inside, when it's under compression, that's why it's buckling. It's too much compression on the wall of the pipe. That is what happens. Okay, this one. So by codes, most of the codes, ISO code and API, American Petroleum Institute, there are codes to prevent pipes with very sharp curves, which can lead to buckling. So generally, is between 3 times the pipe diameter to 5 times the pipe diameter. When in a subsea pipeline, you have to make a curve, say a 90-degree curve. That radius of that curve has to be between 3 and 5 times the diameter. But there are other reasons why, not just because of buckle. Because most modern pipes, they also are designed to have these pegs, these electronic devices that go through the inside and fit closely to the internal diameter. And they go around the pipes to measure for cracks, internal erosion, and all of that, taking measurements. And if the curve is too sharp, they would not make that curve. That's another reason for this rule of 3D or 5D. But as you see even further down, if you have long pipeline paths, they may even have curves much wider than that. That's to try to make sure the pipeline is stationary for seafloor stability. So it's stationary where it's not going to be moved by current so easily with big radiuses like that, much big. That is not for buckling, it's for stability on the seafloor. Okay. And here are some of the installation methods, and we mentioned this because buckling can also happen here. When you install pipelines, the vessel is at the surface, and then depending on the water depth, the vessel has to move very slowly, and it must make a calculated pressure, tension on the pipeline as it's moving to prevent the pipeline from sagging to the point where it's going to buckle in the curve. If you see the S-lay on this side, if the vessel is not 40 to 60 metric tons of pool, depending on the size of the pipeline. Keep it from buckling. Same happens with the other one, the J-lay. At the bottom, it can buckle if the thing is stationary. But the deeper the well, the water depth, the worse it is. Your weight of pipe is on that slope, trying to shorten the radius of the bottom curve, and therefore the buckling chance is much greater in deeper water than in shallow waters. And if it buckles, that's not just a bad day; it's probably a bad week. Because then they have to pull up the pipeline again and try to cut that off and start again. And it's a continuous process of pushing out the pipeline almost as they're doing spaghetti. So equations, I mean, if you go to engineering, unless you are some kind of a research engineering in laboratory, equations is not the main thing that you have to solve, very complicated. Normally we worry not much more than arithmetic and trigonometry. The software we have nowadays takes care of the rest. As far as you know what you put in, you get it out, no problem. But some of the equations I wanted to show relative to buckling is the top equation, which is basically the EI, which is always used in when you look at the compressibility and resistance of steel. So you can see that EI is the moment of inertia times the modulus of elasticity of steel. And then the D to the fourth times nu, that's a fourth differential equation, the fourth level, which is how much that circularity of the pipe is changing if it's becoming ovalized. So you have the equation there, and then the piece of F is actually the effective pressure that that section is C, which could cause the buckle. And then the one below is what is the critical pressure, which is also called Euler's equation, to calculate what is the critical pressure for a pipe of a certain length and a certain moment of inertia. E is always the same on steel, but I would change depending on the diameter of the pipe. So for that, you can calculate a critical pressure. And that's to the 1/3 means the same as the third root, not the square root, but the third root of that equation. So like I said, don't worry about that. You'll probably never see it in your real work. It's just part of some basic principles. But you will see sines and cosines and tangents and things like that. You will see in trigonometry. Here are some examples of potential for buckling. The top one on the left, as I mentioned, is when the sea currents move away the soil that was supporting the pipeline. And so the pipeline now is in the air with a tunnel underneath that could be wide enough to make the pipeline unstable and make it want to fall eventually to that hole because of the weight, and then it can buckle. So that's called a free span pipe. It has no support, like a bridge with no support in the middle. So they can lead to buckling due to the weight of the pipe and the influence of currents. Then you have the other one here. If pipe comes down a difference in height, also on that curve, it can buckle. Because another thing that can make pipeline buckle is temperature inside the pipeline. Stress, thermal stress in the pipeline over long distances. It can make the pipeline shrink or lengthen or expand. And that could be also a reason for buckling. Another one that you see on the right on figure 6 is the snaking, which could be done by currents also. If you have a long stretch of pipeline and it's on an area of mud where there is not much friction, the currents might start moving the pipeline around and it forms this S shape. And so it's by either fatigue or by the shape of that curvature could lead to buckling as well in that case. So you never want to install a pipeline without studying on-bottom stability. And then outside of what we're showing here, there are ways to stabilize it. One of the most common ways is if you buy pipe with a concrete cover, like a 50 millimeter concrete cover around the steel pipe on the outside to add weight to it and to add size to it. So if it starts to slide, it will grab a larger portion of sand that will build a berm as the pipe is sliding, and it will prevent it from sliding very far. Or you can buy these concrete mats. You can buy these concrete blocks tied up as a net sort of, so it's flexible. And you can put this over the pipeline, to keep the pipeline secure to the seafloor. That will prevent buffing or sideways moving, and it will also prevent, if the pipe is light, the tendency to uplift and try to float. That will be another way. Is all of this is pipeline? Yes.
1 minute attention to that.
Oh yes.
Please, this a seminar. It's not because CFI is idle or don't have other presence to attend to.
Yeah.
They are here to benefit you more than themselves. I see a lot of you being distracted on your phone with your AirPod on. Is that you are here for this? That's why we say you should pre-register. It's not free for all. It's only those that are interested that will call here to be here. So if you are not interested, you can as well leave. If you are interested, please, you need to pay attention. This is equally as important as academic program here. So please, I want everybody to be on attention, no sleeping. Please, if you have any issue, you need to go out, please, you can do that. Is that clear?
Yes, sir.
Thanks.
Thank you. Okay, next one. So as we were talking already, the pipeline stability. The pipeline stability you can consider based on two parameters. Either the maximum content density. So the pipeline is either water filled or filled with the product to add to the weight of the pipe. Or you can also consider it with minimum density, which is when it's totally empty, full of air. That's when it wants to float, to come up to the surface. And that is, both cases is a stability situation. If on the first sentence, if the pipeline with the product is too heavy for the soil because it's maybe not wide enough in diameter, it might be a 6-inch pipeline, heavy with the product inside, and the soil is very soft. That's why in our lingo we call it the mud line, because it's all mud, like pudding. If it's too heavy, it will start sinking into the mud. So you don't want it to sink, possibly, and you don't want it to float. So you have to consider both situations for stability. So if none of that is the problem, if the specific weight of the pipe is less than that of the soil, which means the soil is stronger, is no problem. The pipeline will stay where it's supposed to be. Otherwise, if the soil is liquefied, the pipeline can sink. Because when you liquefy soil, that's why it's basically mud, it will not have much strength, much shear strength or compressive strength. So they should be checked, both pipelines, for possible sinking or floating, as I explained. Of course, in some cases, there is a good reason to actually bury the pipeline, especially if you are in shallow waters. You want to bury the pipeline, because otherwise, if a ship launches an anchor or fishing vessels have a drag net coming around, it can be caught on the pipeline and move the pipeline and cause block or cause other damage. Like the dent we saw before, it could have been an anchor or something that dropped on it. So that's always a concern also on offshore. There's all kinds of dangers on offshore. So here is an illustration of the forces that the pipeline on the seafloor is experiencing. Is experiencing its own weight going down. If the soil is strong enough, is exerting a force upward so that pipeline stays on the surface.
There is also a lift force if the pipeline is not heavy enough on a lift up. And then you have waves and current forces, especially in shallow water. The currents at the surface reflect all the way down to the seafloor in shallow waters. So pipelines can be easily moved in shallow waters. That's why most of the times as the pipeline approaches the beach, if the pipeline is coming ashore, you don't want the pipeline to be on top of the soil going through the breaking wave zone because it will be moving around a lot because of currents. They want to drill and put it under the beach to cross the breaking wave zone for the safety of the pipeline and for the stability. And then you have some horizontal drag force, which is caused by the wave and the currents trying to move the pipeline around. And again, you see the one line there. And for all of this, when we are working in this industry, we have a report called the Met-Ocean report and the geotechnical report, two of them. One of them indicates the currents, speeds, the wind force, and the wave sizes for many different years, like 5 years, 10 years, 100 years, or 500 years, wave data and currents. And then you have the soil data, the geotechnical report to indicate what kind of soils you have below that. So that's very important always for the designs of the platforms. Now, this is if you do SAPS, which is the main software for design, you want to specify the wave theory. And this is from API RP2A, the American Petroleum Institute recommended practice way. The applicability of the different wave theories. You have the linear or stream, it's an airy function, normally for intermediate, deep, or very deep waves applicable, not in shallow water. Then you have the Stokes or the stream function, which is applicable a little more towards shallow water, but it has to do with also this ratio of wave heights times the over the apparent periods of the wave times the gravity. So you have to resolve that equation to decide where your point is going to fall in this graph and decide which theory is the one you should do in SATS when you put the wave heights and periods to calculate the most important forces on the structures, on the platforms, for example, is generated by waves and currents and try to create big overturning moments that have to be resisted by whatever is securing it on the seafloor. So that is what you need to look at. Generally, the stream theory, the stream function with the different grades, O11, blah, 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 that one is normally the one that is used almost everywhere because it's good for anything except fatigue. If you do fatigue, we use the airy theory because it's the most simple to work with in fatigue. Is more linearized than the other ones. But this is the way theory is applicable in offshore design. Next one. This is now the lateral stability for offshore pipelines continuing. What happened to pipelines of different sizes and weights on the mud line? Basically, we already described that, and there's another spec there. That's the Norwegian spec. DNV is Norwegian, which is also acceptable international. Is the Det Norsk Veritas. DNV means Det Norsk Veritas. And they give some advice on the situation of how to stabilize the pipeline on the seafloor. And so the displacement will be typically less than half of the pipe diameter. So it means that the pipeline should enter the mud about halfway of its diameter, no more than that, if you're not going to bury it for stability. Next one. That's the end of it. No, that's how friendly we are. Thank you very much. If you have any questions. Go ahead.
So you talked about the mud line versus the seafloor.
Seafloor.
Yeah, is it only silty or is just about when we encounter rocky layers, like the rocky layer, it is not it's not every layer of sand that is silty.
Yeah.
Yeah, so what about when we encounter rocky layer? How can we base our pipeline across that layer?
Yeah. If it offers maybe more resistance against sinking, for example, it's generally mud for 8 meters or so. Below the seafloor is just pure clay, mud. Below that is a mixture of a little mud and sand, starts mixing with sand. Then it can have clay, then sand, and so forth, all the way as you go deeper and deeper. Eventually, it turns into mostly clay or hard rock.
So is it a rare case that when we see rock layer as our borderline, is it rare?
Normally, it's not rock at the mud line is not normally familiar. No, unless you are doing a pipeline over a coral, something's shallow water coral reefs or so. Otherwise, it will not be. It will be mostly muddy, clayey mud over there, which actually makes your piles need to go deeper, because if it was raw, the pile would be having good support right at the mud line.
Yes.
But because it's clay, the pile only encounters support about 10 meters or so below the mud line, because on that 10 meters of soil, the pile is still moving laterally with the loads on the platform. It's not fixed like in concrete.
Yes.
It has to go further down. But if you had a soil with sand, the pile will be already resisting a lot more right by the seabed. So it will be better to have sand. But unfortunately, the case is not that. It's mostly mud.
Well, sir, you mentioned that for the mud line, that is where we have mud. It has to be, it was not be buried fully. Like, it has to be like after buried, but not buried fully. It will be the ground.
You mean bait?
Yeah, no, buried.
Oh, buried.
Buried.
Oh, buried, yes. Yes.
Buried, you should be after you buried into the ground. If it is silt.
Yes. You can have it buried or not buried. If you don't want the pipeline to bury itself and let it sit under its normal weight for about a half of its diameter, if it cannot do that, then you may have to put a stabilization platform underneath it. You may have to put some stone gravel or some steel plating to support the platform and spread the load over a larger area to prevent complete burial.
And to prevent fatigue as well.
Yes, because if it doesn't move, fatigue has to do with continuous motion, continuous vibration. If there is no vibration, there is no fatigue. If there is also, say, tension always, and no reversal from tension to compression, there is no fatigue. That's why they put the bolts when they tighten flanges of pipe sections. When they build a pipeline, you have the flanges connections, and they always torque those bolts so that they are in tension. That is to prevent any fatigue, because the bolt is always in tension. Doesn't matter if your pipeline goes into a little compression or not. The stress in the bolt is always tension. That does not reverse. And if it does not reverse, there is no problem with fatigue.
It's already beyond the passive state. The intention.
Yes. It will, as long as it's always in tension, it will not have a problem with fatigue. Fatigue is because of reversal of stress from compression to tension, tension to compression on cycles. That's what causes fatigue.
That's not one more question. Is there a mention about flat things more?
Yeah, from the hydrostatic collapse of the pipeline. When the pressure outside the pipeline in deep waters, the outside pressure of the water, because the pressure is the density of the water times the height of the column of water above the pipeline. That pressure, if it becomes more than the hook stress capability of the pipeline, then the whole thing will just collapse all of a sudden. It will just collapse. So that will be the case like that. You have to consider the water pressure outside versus the pipeline pressure inside. If they're not similar, you could have a collapse. And SACS allows to check for that also. And one thing you can do, you can put an external ring every so often in length. Put external rings. It will prevent collapse. All right, looks like we have some movies to see.
Thank you very much.
Short one.
Please,
Someone is asking for
So, should we allow one question, two questions? So go ahead, please.
That's the microphone. I think he wants to know about software.
What's software
Design.
for structural? Is SACS, SACS,
SACS.
SACS. It's sold by Bentley. Bentley that owns a lot of software is in a way similar to STAT, but is better for the offshore because it allows you to put files, to put the wave data, to put the currents, the wind. And I don't think STAT Pro allows all of that. But otherwise, it's similar. It's similar. Now, for others, for like installation of pipelines, there are other softwares like Orcaflex. There is another one, European one, that goes well with SACS for higher level analysis, like collapse analysis or time history analysis. That one is called OSPOS. There are so many softwares nowadays. But what we use offshore is generally SACS. That's all right. Thank you.
Yes, the question.
Any other question? Yes, sir. How much active can then be considered as cracks caused by corrosion?
Again,
Then because as cracks caused by corrosion.
no, the dent is not caused by corrosion. A pit might be caused by corrosion, like a perforation or an indentation, but because the metal went away, not a dent. But corrosion does eat away the wall thickness of the pipes. Yes.
But because corrosion causes buckling as well.
It could, yes, because it would reduce the wall. So it could make a normal.
Hey everybody, this is lecture.
It could reduce the length of the pipe as a column, and so increase its slenderness because it's the ratio of the length versus the radius of gyration, and the radius of gyration implies the moment of inertia, and the moment of inertia means that the thickness of the pipe enters into the equation to calculate the moment of inertia. So you reduce the thickness, you reduce the radius of gyration, you increase your slenderness. Very good question.
Thank you very much.
You're welcome.
Yeah, that's fine. Is that something? Well, something. Yeah. There's no point solution.
Yeah. That's you know.
Is that something?
And at the end is my abilities with language.
Number 4 for the subsea pipeline design. Hey everybody, this is lecture number 4 for the subsea pipeline design section. And in this section, we'll be looking at span analysis. So pipeline.
You know, you're all disconnected.
Question.
And spanning occurs when the line loses, when the contact between the pipeline and seabed is lost over a considerable distance. So if this occurs, It's normal code requirements require that the line be investigated and checked for excessive yielding, fatigue, and clash with human activities, and these may include like fishing. So this is just a schematic, just a representation of some spanning. So you may have the seabed over here, seabed, and there may be some change in elevation. So the pipeline loses contact with the seabed. And this is you have the self weight of the line. And you may have some longitudinal load. And then, so the span length is shown over here. So if the span length is, it's of a considerable distance, then there could be some issues that arise. So as a designer, you have to take a look and calculate an allowable free span. How much are you not going to allow? And if the actual free span is greater than the allowable free span, then corrective measures must be taken. And these corrective measures can be very expensive. And these corrective measures are intended to somehow reduce the span. Reduce the span. So because it is so expensive to take corrective measures, it's very important that that the analysis be realistic and that the engineer takes it into account the actual seabed conditions and doesn't assume something that's too conservative, because that will lead to greater costs for the project. So when you have a pipeline span and there's some type of wave and current flow around the pipeline span, especially perpendicular to the line, it generates sheet vortices. And this shedding, vortex shedding from above and below, causes the pipe to oscillate up and down. And so you can see in the figure, you have these little vortices coming around, and these leak, and these may cause a pipe to oscillate up and down. So the vibration direction is up and down. So the key thing here is to make sure that you avoid resonance. And resonance is when the frequency of the vortex shedding equals to the natural frequency of the pipeline span. So if resonance occurs, the vibration can be amplified greatly. So the displacement of this pipe can move up and down a relatively large distance. And an excessive vibration, especially large distance vibration, can lead to fatigue failure and cracking of the concrete coating, if there is concrete coating. So typically, shedding frequency, the calculation of shedding frequency is done using traditional mechanics, but you have to also take into account the effect of the seabed and how close it is. So take into account the effect of seabed. And then the calculation of the span frequency has traditionally been done using simplified models. But recent theories have suggested that these simplified models may be multiple span analyses too simple. So for that reason, multiple span analyses need to be performed. And this is the end of lecture 4 on span analysis. Thanks.
one major difference between being in the estuary of a river or being away from a river in the ocean. This one is repairing pipeline and a city. You can see videos where they have a lot of automation to repair pipelines on the seafloor. And they have even somewhere you can go there and they put a big chamber around the pipeline. They exhaust all the water and the guy is welding in an atmosphere inside with the pipeline entering one end of that enclosure and leaving the other end, and he's performing the work in the middle, in the sea, under the water at some depth. It looks like what they're going to do on this one is a hot tap. They're going to perforate and attach a T with the pipeline in function. We're not talking the pipeline flow inside the pipeline. So now they have a T branch right there. Hot tap. They're putting a plug inside the pipeline to isolate some part of the pipeline by stopping the flow. So as you can see, they're going to remove that buckled area. machine. If it has any electronics, then they call it an intelligent vehicle. So the buckle, the misalignment has been replaced straight by. And I believe this is it from our side.
Are you taking a session? You're taking a session.
Good Charlie, social media manager. So stay connected, CFI. So here, how can you stay connected to CFI? Our socials, you can find us on LinkedIn, Instagram, YouTube, or Twitter. I'm just going to make this a few seconds. LinkedIn, CFI Services, Instagram, CFI Services UK, YouTube, CFI Services, Twitter X, CFI
underscore services. So I don't know the people that were here and doing YouTube. What do think everyone is here for? The first 10 people to follow us on LinkedIn get something from us. So, and also the first 5 people on Instagram, YouTube, X also get something from us. So, for like 10 seconds, just follow, you turn off the phone, you can follow. So, what to expect on our social media platform? Educational, engineering, and subsidy videos. If you go to our LinkedIn, you see a lot of educational videos. A lot. So far, we have worked like 20 uploads. Industry insights and technical tips, projects highlight and innovation, and things like our workshops and like our project. We have workshops, so you can see that also. Training opportunities and professional development. So for students, if you want to like graduate CFI, I think it's very important to follow us on all our social media platforms because we will be the first to post it when we are accepting new trainees. So students and anyone who wants to trainee at CFI, you have to follow us first. So you know when exactly we are accepting new trainees. And also, we have continuing education courses on our website. Currently, that's at 98%, more like it's done. Just want to put it up. So if you follow us on our website, www.cfiservices.co.uk, we're going to have a training link there where you can get courses, buy courses from us just to expand the knowledge in the engineering world. And also, our company updates and events. So we're not just work. We have team bonding sessions where we put like colleagues being close to each other and working very, very hard. So yeah. So we at CFI, we just want to like with everyone to just grow with us so you can stay motivated. Thank you very, very much.
I believe Chama should come and talk now. What Chama to come and talk? Okay, she's coming ahead. Clear the good for her.
Greatest engineering students. Greatest engineering students. Greatest of the greatest engineering students. Good afternoon, everyone. And I must especially recognize my project supervisor. I'm sure he's going to laugh and tell me to stop it. That's engineer Professor Akombo. Yes, he remained my project supervisor when I think that was 2000. Yeah, 2000. So, students, this is being brought to you with the huge support of CFI. CFI used to be in this classroom with me. So you can see this CFI, this is me, and we thought to take our alumni with us everywhere we go. So we must applaud CFI. I know they've been here since morning. How many of us were in the first session? Sorry, how many of you were in the first session? Okay. I would say I congratulate you for you having the opportunity, because once we're in school, maybe some of these things were not really so common, and we felt the need to let the town meet the gown. I'm sure some of these things that you are learning and the things you learn in the morning are not things that ordinarily will come to you during your courses, right? Yeah, so the essence is for the town to meet gown, so that when you are out there, you will be able to relate with what you learn in school. Also, like it has been rightly highlighted, that you can follow CFI, request for internship opportunity, and I've told Victor, prepare for it. So part of the collaboration we've been doing, many of our young engineers have actually had the opportunity of working with CFI. They have limited space. So if you're going to apply, be really sure, be very, very sure that you are there, because I feel a bit disappointed. Half of you were on your phone when the lecture was going on. Some people were sleeping, some were going in and out, and I see Professor Lawrence coming to tell you to stop it. Like I do tell people, everything is an opportunity. I never envisaged this when I was coming in as the chairman of NSE Ikeja branch. And the way I talk to people about what we do and the need to make impact, birthdays, and so many other things that CFI is doing for the Nigerian Society of Engineers Ikeja branch, amongst other things to engineer. So please, there is also someone behind there. He had his headphone on throughout. Yes, he's looking at me now. He had his headphone on. They told him to stop and he was busy. Virtually all of you were on your phone. So it's really up to you. Let's make good use of every opportunity you have, so that in the future, you can also be on this side of the podium and be able to give back. So I congratulate you for coming here, and we do hope that we'll sustain this with the alumni and any other organization. I know CFI will still come back, but there are still a lot of our classmates that are doing very well that we hope to bring them back. But it's important that we also reciprocate by being present, by being intentional about our growth, because we want to be sure that when you come for internship or when you come for interview, you are not only coming on the platform of, I know my senior, or I know my senior can connect me there. You want to be able to say that you really deserve that position and that you've merited it. So once again, congratulations and thanks to you.
It's our work.
I have to say, it reminds me of those days when I finished prospects. We both finished the same year, 2001, civil engineering. And we had Professor James at home. We both did our final year, what's it called, project under Professor James. Please, acknowledge him.
Come and stay with us now. Sorry, so the interesting thing is that you eventually, it's a small industry, as big as engineering is, the small industry, and eventually become colleagues. So we are all not, sir.
Let me speak now. You see, these are my bosses. Let me tell you, and God's willing, this will come. You also take over. I'm not part of those who will get out. Come here. I see you as leaders. And they've done what, let me tell you, when Victor said this thing to me, I said, I'm on top of my way out to engage to come and meet separation. Because when I saw the two of them on the same banner, I said, my chair and my leader, they are going to UNILAG. No, whatever I'm doing, I'm going to be here. And I want to say thank you for you particularly and your team. They have a group, and the message I'll pass to you now Maybe some of you are final year, some are third year or fourth year. The future is bright, very, very bright. But it only depends on the way you play it. She said it all. See how many of you are busy with the phone, headphone, new phone, and so on. Don't lose opportunities. You wouldn't know when you are losing it. Like she said, yeah, as a chairman, I know you before will not come in. Come to real job itself. Your skill. I give people these three letters, A-S-K. First is A, attitude. This is talking about the way, your attitudinal way of acting, coming, not listening. S, your skill. The skill. When he was giving a lecture, talking about the bottling, just remember the elasticity and so on. Then when you have plastic information and so on, was watching how many of them are really listening and try to appreciate what they were taught in their classes and the real reality as it is. Not the white BS and plastic equation that you are busy with. This is in practice. Please pick it up, and I want to wish you all the best. College friend. Don't single time. I call any of them, they answer me. I was not too good to them. Let me say it clearly here. I was too stubborn to them. When they are here, but they are my friends tomorrow. Till the time itself. Thank you so much. Thank you. Thank you.
Well, on behalf of CFI, I just want to say that it's first of many sessions. I know the current ESCOs of their way. I will be more than happy to work with the next set of ESCOs and continue the culture where we started. We've always wanted to be involved, but we didn't know how to be involved. But this is kind of like giving us a way into the system. There's a lot of training materials. Feel free to reach out. We could always send a link to a member of the ESCOs and they can share the link with the rest of you guys. No knowledge is lost. I would have expected in a training like this, do not be shy, just ask your tough question. No question is dumb. We're not anticipating that you know whatever Engineer Louis was going to speak about, but it's an opportunity for you to even ask, what is a pipeline, for example, right? How is it different from the plumber? A plumber comes in, remember, they're changing one piping line to the other, and it says flange. Imagine yourself, so we used to call ourselves offshore plumbers, because that's what we do. We just lay the lines, and then you join them by a flange or the other. But it's a journey, and a journey of 1,000 steps starts from the very first step. And that first step is to take your course very serious. The models you're being taught now are essential. They will say models, you know the current international airport. The current international airport is being refurbished or renovated, right? Has anyone been there recently? The Monitor International Airport. It's a big project. Guess who the project manager is? It takes a solid foundation to get to what she's doing now. And everything we were taught was from this same room. We have the same opportunity. So don't limit your thinking. Do not limit where you could be from here to tomorrow. And like I mentioned earlier, for the oil and gas space, if you're looking to cross over, if you're tired of the building designs and all that, there's a number of transferable skill sets across the discipline, not just civil engineering, which we showcase in the first session. So if you missed that, we're happy to replay that again to another crowd, those who missed. Feel free, just nudge us. We'll always create time, even if it's weekend. Spoke to Joshua. This is what we're passionate about. We want to bring back that knowledge, skill set back to Nigeria. It's good to see disciplined engineers play with software. When I was in your shoes, I used to turn my screen around, look at the structure this way, that way. There was passion. So you have to pick that back. To pick that back, you have to capture it. In our midst today, our work, we have people who have not served yet, right? We went to NSE, they advertised, there were full of people, they interviewed. None of the people they submitted to us not even done their service. They're fresh from university.
But when you listen to them speak, you think they have 2 years experience under their belt, and they haven't even done service yet. So that's the kind of opportunity we offer. And I'm not saying we have a big space until everyone, but we're happy to support, even if it's an inquiry, even if you say, I want to go do a master's here, I don't understand which of these courses can we do, different schools. So we're there to just, provide that, support when necessary. I hope you've enjoyed the full day. Like I mentioned, there's plenty more to go. We want to have more technical sessions. We could bring in topics that are much more bespoke to what you study, maybe the option platform design, which is similar to the design of the building structure and all that. And we can take it from there. So thank you, NSE. Thank you, SES. Thank you for everyone for attending, and I wish you a safe journey back home.
Thank you very much, Engineer Victor. Thank you very much, Engineer Louis. Thank you very much, Engineer Nemo. I think the next thing on our agenda is just the closing remark by the U.S. president, but he's presently not here, so I'll just take that on his behalf. Then after that, we'd like to take a group photograph. So we're going to use that. So we're going to use we will run on our feet. Then the window panel will be at our back so that can capture CFI and also NSE also. Then we'll take a group photograph. Is that cool? So for the closing remark, on behalf of the U.S. president, we would like to express our sincere gratitude to CFI Engineering Services, to NSE Ikeja branch, to UNILAG Faculty of Engineering and Alumni Association for organizing this insightful seminar. And also to our Dean of Engineering, Professor Eswa, and also the hosts who supported this program. We would love to appreciate him, to Engineer Nimot, to Engineer Louis, to Engineer Victor Ike. We really appreciate you for sharing your expertise and willingness with us today, and it has truly been memorable. The topic offshore pipeline global blocking has opened our eyes to the real world challenges, and that it awaits us as future engineers, and we leave here better equipped than we came. As students, we are reminded that engineering is not just theory in a classroom, it's solving real problems in a real environment with real pressure. So I want the engineering students in this room to echo this with me. Are you cool? Are you cool? So dear Engineer Victor, dear Engineer Nimot, dear Engineer Liu, yes, CFI, we hope to see more of this in our faculty. We hope to see more of opportunities. And we commit to carrying this lesson from today into our studies. Engineering was that a yes to us, Victor, is that yes to us, Engineer, is that yes to us, that we'll see more of this. Is that a yes, sir? Okay, thank you very much. So let's do the round up there. Thank you very much, every student represented here. So just quickly, we're going to all rise on our feet. Distinguished delegates would, that's Engineer Victor, Engineer Louis, Engineer Nimot, we will all stand at stage here. And the window banner will be at our back and take a quick photograph. Is that okay? Yes. Okay, so let's please rise on our feet.